Now let's understand the property of viscoelasticity of the polymers or plastics. Now this is a very critical property which differentiates plastics from the general engineering metals. So let us consider a coil spring which is under load, that is a load F which is applied on a coil spring which is fixed at the top. So the coil spring will extend. Once the load is removed, it will oscillate and come back to its original state. So the final state and the original state will be the same. This is purely elastic behavior. So if we take the graph over here of force versus deflection, as the force is applied, the deflection will occur of the spring, and at this point when the force is removed, the deflection of the spring will come back to zero. So this is purely elastic behavior. So this diagram basically denotes the action of that spring. Now if we are having a dashpot in parallel to a spring and with the same setup, that is fixed at the top and loaded at the bottom, then what would be the result? So a dashpot is basically a shock absorber or a damper which we use in the suspension system. The suspension system consists of a spring and a damper. And basically the function of the suspension system is to reduce the vibrations which are coming from the road. So it does that by absorbing the energy of the vibration. So the spring will allow it to vibrate, and that energy of vibration is absorbed by the damper or the dashpot. So a dashpot is a mechanical device which is used to resist motion. So this dashpot will resist the motion which is taking place through viscous friction. The viscous friction is generally created by the restricted flow of fluid. So for example, if you take a damper, a shock absorber which is used in vehicles, and if you just open it up, you will find that the piston has orifices in it which restrict the flow of the oil from one chamber to the other chamber, which basically results in the viscous friction, and hence that is the function of the shock absorber. So that same damper or shock absorber is shown over here as a dashpot, and it performs the same function. It basically acts as a resistance to the motion due to viscous friction. If we plot the force versus deflection curve for such a system, it will look like this. So it will start from the origin and it will go to this point. Here the graph is not a linear line, but it is a curve because of the combined effect of the spring and the dashpot. And once it reaches this point, the load is removed. When the load is removed, it will tend to come back to its original state, but it will not follow the same path as earlier. It will follow this path like this, and this region in between the loading and unloading cycle is called as hysteresis. And this is nothing but the energy lost in this cycle. This energy is generally dissipated as heat because of the friction. So if we take the examples of the suspension, so the shock absorbers under heavy operation will generally heat up. So that heating up is because of the viscous flow of the oil through the orifices of the shock absorber or damper. And that is the hysteresis loss which occurs. So because there is a viscous friction effect which is contributing to the energy loss, this type of model is called as the viscoelastic model. So it is not a pure elastic model, it is called as the viscoelastic model. And the behavior as shown over here by this graph, which shows an area enclosed, which is basically the energy loss. This type of mechanical behavior is called as viscoelastic behavior. So the dashpot generates heat, it dissipates the energy because of the hysteresis loss, and the amount of energy dissipated is given by the hysteresis loop. So this hysteresis loop, which is connected by the loading and unloading cycle, will have a certain amount of area on the graph enclosed within it. So this area, the measure of this area will basically give us amount of energy lost in the system. As in the case of the shock absorber, which is used in the suspension application of a vehicle, this viscoelastic behavior is used as a benefit or a desirable characteristic of the system. So it is used such that the energy should be absorbed, energy should be lost, that vibration energy should not be transferred to the occupant. That is the main function of the shock absorber. Whereas in the case of materials which behave like a viscoelastic model, in that case, this viscoelastic property may or may not be desirable. It would mainly depend on the application for which it is used. So if we replace the spring and dashpot with a equivalent material which is under load. So basically this model, the spring model, can be replaced by a steel beam or a steel block, it will act like a spring. If you take a steel block and if you attach it at the top and then load it at the bottom, it will behave like a spring. But only thing is that the stiffness of that block will be very high as compared to an equivalent coil spring. Similarly, a model which is having a spring and dashpot in parallel can be replaced by a equivalent viscoelastic material. And that material is nothing but the plastic which we are studying. So it will have the inherent spring and dashpot properties, and it will have the viscoelastic behavior in which there will be energy lost due to hysteresis. So the plastics or polymers will exhibit this type of behavior at the micro level, which is internal to the material. So in plastics, there is no separate spring and damper or dashpot. Both of these are generally integral to the material and the behavior is observed for the plastics. Whereas metals generally behave as elastic springs. So from this we can understand that the strength of materials approach for analysis of structures is based on the fact that we are using elastic materials for our analysis. Elastic rigid materials. That is the main assumption which is used for strength of analysis studies, which are generally used to design structures, steel structures and metal structures. But when we talk about viscoelastic materials like plastics, which behave in such a manner, the assumptions and the variables which we have to factor into design will change, and hence we have to apply the strength of materials principles very carefully when it comes to plastic design. So as we have seen earlier, plastics generally have some amount of permanent deformation which goes along with it. That is because of the viscous flow which happens in the material. So that permanent deformation is shown over here in this graph. So this is the loading graph and then this is the unloading graph. And the gap between the zero strain to this strain over here at the end of this curve is the permanent deformation which occurs at the end of loading and unloading cycle. Here is a complete loading and unloading cycle with reverse loading as well. So this gives a good idea of the behavior of the plastic through the complete cycle of loading and unloading. So here the graph is having the deflection in the x-axis. So in the x-axis there is positive deflection, there is negative deflection, and then there is positive load towards the upside and negative load towards the downside. So it starts with the point O, which is the origin point. The loading starts. So from this point it goes to the point P. The curve is non-linear, and at point P the load is removed and reverse loading starts. So at point P, when the load is removed, it will take this curve, and when the reverse loading is beginning, it will start to continue for this curve, and it will end at point S, which is the reverse loading limit of the test. Then again the loading will be reversed towards positive loading. So when the positive loading starts at point S, it will take this path, it will keep on continuing on this path and cross the x-axis at point T and then continue towards point P again. So this will be the complete loading and unloading cycle of the plastic. Important point to note that when it returns after the load has been removed, the point Q and point O are having some distance in between them. This is that plastic deformation which we are talking about over here. So when this loading cycle keeps repeating, we will find that this curve is being created again and again for each and every cycle. And this loop which is created, which is connecting S and P, will form the hysteresis loop, and the area under this loop will basically give us the energy lost. So the area in this loop will give us the energy lost in the material due to the loading and unloading cycles. And that area inside the loop, that is the energy lost, will tell us how much inherent damping does the material have. And that is a very important property which we have to consider in design. Generally, glassy hard plastics will have minimal damping behavior, whereas flexible plastics and ductile plastics will have more damping behavior to them. So just to go through again, the loading cycle starts from O, it goes to P, and then it goes from P to S through relaxation and loading in the opposite direction, and then from S to P again it goes with the loading in the positive direction. So the load deflection curve is indicative of the viscoelastic nature of the material, which is exhibited by most of the engineering plastics and elastomers. Important to note that heat generated due to this hysteresis loop will adversely affect the mechanical properties of the plastics. So this hysteresis loop will create energy lost, and that energy lost will be converted to heat and hence increase the temperature of the plastic, which will in turn affect the mechanical properties of that plastic. Also, along with temperature, as the number of cycles increase with respect to time, that is for high strain rate or for high rate of loading or frequency of loading, the behavior of the plastics will also vary. So in summary, the viscoelastic behavior is very important characteristics of plastic materials, and that viscoelastic behavior is highly dependent on the rate of loading, the frequency of loading, as well as the temperature and heat which is generated. Hence, for structural applications where there is a high vibration and there is a structural integrity which has to be maintained, plastics are generally not preferred because of the high vibration, high rate of loading. They will generate heat, and that heat will in turn degenerate the properties, the mechanical properties of the plastic.